Okay. We have our thickness of material. That's the material. That's the thickness. Delta X. And then P is the rate of energy flow. That's the energy flowing in. You can think of it like water flowing in, volume of water flowing in and then flowing out. Q1 is the where it enter. That's the theta 1, temperature on entering. Theta 2 is the temperature where the heat leave. And the temperature must be greater as you enter. So theta 1 is greater than theta 2. So theta 1, delta theta, change in temperature or difference in temperature is theta 1 minus theta 2.
Oh, isn't it theta 2 minus theta 1?
Theta 1 minus theta 2, the larger minus the smaller.
Oh, okay.
Okay, so I just define a term G called temperature gradient. It's just minus delta theta, delta X. Negative shows that the temperature decreases with distance. As it increases the distance, the temperature decreases as well. And then the unit in this case, theta is Kelvin, X is in meter, so it's Kelvin per meter. Then rate of heat flow, right? It's normal to the surface. Is proportional to cross-sectional area. That's the cross-sectional area where the heat enters. Temperature gradient. So we can play with the formula, okay? So they can memorize the formula minus K AG, or you can call it CAG, or GAK, whichever you want. Now to memorize the formula. K is called the thermal conductivity. So we can define thermal conductivity by rewriting the formula. Can be defined as the rate of energy flowing per unit cross-sectional area per unit temperature, different temperature gradient. Okay? We are just using this formula to define P per unit area per unit temperature gradient.
And we ignore the negative.
Say again, don't want to worry
We
about
ignore
negative.
the.
You don't want about negative. Negative only comes in when you looking at the temperature, want to draw the graph. So P is in watt, A is in area, meter square, G is the temperature gradient, Kelvin per meter. And simplify. No need to memorize. Go and derive it. W meter minus 1, K minus 1. Right? Don't need to worry about the different value. Don't need to worry about the last column. This one is just telling you the thermal conductivity is that depend on temperature. So this is taken at temperature 25. Examiner will give you, so you don't have to worry about all that. Metal, example, copper has high thermal conductivity. Yeah, that's a copper. And diamond also. Air has low thermal conductivity. Or styrofoam also the same. Air or styrofoam, which is a non-metal. Why air got low thermal conductivity? Because the molecules are far apart. So
And they are non-metal.
They're not metal. So collision thermal conductivity is more of, in this case, it is a insulator. So they collide to transmit the energy. So they are far apart, so it takes time to collide. And then the number of molecules is also low. Number of molecules per unit volume is also low. That's the reason why it's a poor conductor. Okay, thermal conduction in insulator rod, 8281 in your book. Insulator, or sometimes we use the term lagging. Perfectly lag. Right? That means no heat is lost at all. So if we are going to look at the graph of temperature gradient against the length, you get a straight line. And the temperature gradient is constant. We will want to draw. Basically, the heat goes in, the heat come out. Same.
Yeah, heat is not lost, right, teacher?
Say
when
again.
it's in the insulator. Heat is
It's
not
better
lost
not.
when it's in the insulator.
Say again.
No heat. See, I mean like the thing passing through the the rod where got insulator both sides. They don't lose it, right? So
They
basically
don't
the
lose on the side.
temperature.
They just go straight through. The water flowing straight through. No leakage.
Yeah, I mean their temperature like constant, right? It won't like how
Temperature
you
is
say
not
they don't
constant. There's a temperature
increase.
gradient. Yeah, it's going down. Straight line.
Straight line. I mean like
Straight
there's
line.
no loss or increase or anything, right?
Right? We can rewrite the equation, or you can look at this graph itself. Right? This graph itself. Right? So we can rewrite the equation. That's the equation. And then take the x across, take the Ka down. Right? Ka down, and rewrite the equation. Take the theta across, take the pKa the other side. We got negative side there. That's the equation of this straight line. Okay? Negative gradient. So this is the gradient. So the gradient is determined by K. If K is larger, gradient is going to be gradient is larger. What happened to the gradient?
Okay, it's gradient larger.
It will be smaller, no? Huh?
Yeah, the K will be smaller lah.
Important. This is the application part where they decide to draw the graph. Inversely proportional to K and A. Slope less. Okay, so this one we are looking at theta 1, and then we are taking this as your origin. And then x is the distance from this end there, the left hand end. Or we can use this formula directly, no? Differential equation. And d theta dx, d theta dx, this is your p. It's just p over ka. No? Either one, can you either derive it or use from this equation directly. Anyway, yeah, gradient is p over ka. If you look at temperature gradient against length, it's constant, right? Because it's a straight line graph. So it means that if you take the gradient is constant. No? Memorize, that's all. Non-insulator rod, page 283. Right? It's just like a pipe that's leaking now. Not insulated means it's like a pipe leaking now. The water will leak out. So at the end there, you may not have any water coming out if you leak too much. So the rod is not insulated, heat is lost from the side. Right? Maybe only one will go through or none will go through. Right? The others will be lost at the side there as it goes along. So a graph of temperature along the rod against its curve is a curve, normal or straight line. Right? A lot of it lost. So temperature becomes lower and lower. So somewhere along here, we'll reach the temperature, room temperature, right? Theta 2, if the room temperature is theta 2, temperature gradient decreases, is the slope. Remember, temperature gradient is a slope, so it decreases. So it decreases at the end there, this part will be theta 2, depend on how fast the heat is lost. So we have done this question. What's the answer?
Okay.
Unlike
The answer is C.
okay.
If it
You
was
just
lag means the answer would have been A.
yeah, lag will be A. You memorize, that's all. And then this is if the surrounding temperature is less than T naught, it will go down first and then go up again. Right? Must be able to recognize this one also.
Go back again, che. So what do you say about the donkey?
Donkey is if your room temperature or the surrounding temperature is less than T naught. Right? So it will lose all the heat to the room temperature. And then it will go up to
If
the,
room temp,
yeah, it will lose to room temperature. And then it will go up to T naught again.
D happens if room temperature is less than T0 lah. That's
Yeah,
all right. So
yeah,
it's trying
yeah.
to tell. Okay.
Must be able to
Okay, Racha.
recognize.
Mm.
Okay, this is your quick check one. Page 284.
But the answer cannot be boy because it's like going like very slow, right?
Very
Actually,
slow. Usually it looks very fast if it's unlike if it's very long. Yeah, see, N is long. T is long.
I mean B also correct lah. But then if it was fast means they only the answer
D
would have
is
been
if
correct.
the surrounding temperature is less than T naught. That's your D.
Surrounding
Then
temperature
this
is
one,
less than T naught. Okay.
first part is not
This one.
lagging. No lagging.
Oh, just a minute, Acha.
Should be able to get the answer straight away, very fast.
Yeah, just a minute. Uh, A and boy is wrong. The answer should be C.
And it should be smooth. Not like here. There's a jacket there. Not like
Yeah.
you lose it very fast.
Hey, wait. So, like our previous question just now, donkey, right, is unacceptable because it is losing too fast and then only increasing, right?
D is because it's not a smooth. It should be smooth. Right? This is not smooth. It show you it's sort of like going down and then going slightly jagged there, which is wrong.
Wait. So, like our previous one also is not smooth, lah. Actually.
Previous one.
Yeah.
Previous one is what's the problem?
Donkey is also not smooth,
Donkey
right?
is if the surrounding temperature is lower than T naught. This is the surrounding
Oh.
temperature. T naught is the surrounding temperature. That's why you get C. But if the surrounding temperature is less than T naught, then you get a curve first. It will lose all the heat and then it will heat up again.
Ooh, okay.
Right? You should be able to calculate, learn to read. Right? This is your K. Just get using the formula, that's all. Right? That's your
P equals
formula.
to K
That's your
AAG.
K. That's your P over A. Right? P over A is given. Then you are given your X. So you want to find the change in temperature, that's all. Put in what is given and calculate out. Okay. Okay now.
Just a minute, sir.
I thought we had written already last week.
Yeah, I got it, but then I forgot to write down.
Learn to read. All right. Learn to read the question. Find what is K, what is given there, and then what is your X. Remember to change your to meter. Change your cm to meter. That's the important thing.
Okay, sir, can go to the next one.
Number 7, you just think of it as each rod is like a tube there where the water can flow through. So you calculate it for each of the rod and add them up. Just use the same formula. P is Ka. Don't worry about negative sign there. Put in your value, your K value. That's your K value. And then there's your cross-sectional area for the first one. And then your temperature gradient is 20. And then the length, 0.4 meter. Then after that, calculate for the thick rod, this one. 25 times 4 times. 25 is same, same material, and then you are told 4 times the area, so times 4. This still is the same. Calculate out, then add it up. Okay. Okay with that? Okay with that? Quick check one, page 5, number 8.
Yeah, and then we just champu it, right?
Just add them up. If it's parallel, think of it as a water flowing, that's all. You have to find the flow for each pipe and then add them up. Okay. If you're okay, then you should be able to try the next one. All right. For the rod parallel, the flow rate depend on, right? Depending on each of the area, that's all. Then add them up. You should be able to try this one.
Wait, 1 minute.
We check for number 4.
Go back again, sir. Okay. Next one is quick check forward.
Number 4.
Okay.
Make sure you understand how to use the formula first before you go further. No point in going over the theory and then you don't know how to apply. The same, apply for each rod. The P is the same. P is constant. And then put the two of them equal, that's all. Okay, EA. And calculate for metal rod X first. Let the temperature, the boundary be theta. Right? Calculate your K, A, 100 minus theta. Length is 40 cm. Right? So here we are not worried about actual value. We are finding theta. So we don't have to convert it to meter. We can use cm. You want to convert meter, go ahead. Right? It doesn't affect the answer. And calculate for py. Ui. Right? As long as our unit is the same, we are okay. Right? You are told that they are the same length. Sorry, they are different length. One is 40, one is 20. That's the reason why we read 20 here, 40 there. Same cross-section area. Same cross-section area. Yeah, the joint rod is lagged and the opposite end are kept at 100 and 0. 100 here, 0 here. Thermal conductivity of K is twice that. If your X is K, then Y is 2K. That's all. Then put the two equal. EX equals BY. The same flow rate doesn't change. Flow rate is the same in the metal. And substitute this value in. Cancel the KA. Then cross multiply. Cross multiply. Then calculate our take across there. 5 theta. Theta is 20. Answer is A. Can. Can or not? Can get the answer.
Just a minute. Wait, so the KA we don't do anything lah.
A, we cancel off on both sides. Or you can take the KA down, then we'll cancel off.
Oh yeah. The A are the same cross section.
Ah.
What? So no need lah.
And you take the 40 across there, 40 and 20 cancel is still got 2 times 2 is 4. And this is 100 minus theta.
Sure, but the metal Y part, the what's that? The G part, I don't get it. Sure, like why you do theta over 20?
This one is for y. This is your y.
Oh yeah. Theta
Theta
minus
minus 0.
0. Yeah. Okay. Now it makes sense. Okay.
Right? For rod in series, the rate flow is the same. Yeah, you should be able to tell me the answer for this one.
Go back again, sir.
Okay, we need to change to a new one in a while. New zoom in a while.
Oh,
Okay.
um,
Okay now.
yeah, wait sir.
Why so slow?
Teacher, how did 100 minus theta equals to 40 theta became 20, teacher?
What do you mean become 20? We are just doing
No,
that.
below there your answer.
This one take across there, it becomes 5 theta. 5 theta, 100 theta is 100 divided by 5 is 20.
Okay.
These are all your maths problem, that's all. This is this part, after that is your maths problem. Yep, what's the problem? Any more problem?
No, I'm okay. Next, sir.
Okay. It's lagged, X and Y lagged. We call it composite rod.
Sorry, sir. Can you go back again, sir? Okay. Oh,
All this you must be able to calculate. And the only way is go through the question. If you don't know, don't go through a question, you lose it. Practice, then you know. It's just like maths. You don't practice it, you lose it.
okay, sir. The next one can go.
Right? Composite rod, two rod, X and Y of the same length, same cross-sectional area. The composite rod is
Just a
well
minute, sir.
lagged, and the temperature at the ends are 100 and 0. The thermal conductivity of X is twice that of Y, which are falling graph.
Just give me a minute, sir.
Playing with the formula, that's all.
Okay.
How is thermal conductivity related to the gradient?
The answer is boy.
How to be boy? They
Hey,
are
no, no,
not.
no, 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 no. The answer is donkey. Yeah.
How to be donkey?
Mm.
Right? 100 minus theta or x. We are just using the same formula, or straight away go to the gradient. Gradient. Right? You are told that x is twice, so it will be less steep. You are right, donkey. No need to go so much there. Less steep, that's all. Greater conductivity, less steep. That's all. That's the gradient. Use the gradient. Okay. No need to go so much calculation. Objective one, you just know that what is your gradient. Okay now.
Okay.
Okay. How do we measure the thermal conductivity of copper? We call this method Shear's bar method. Page 286.
Yeah. Sorry.
Okay, I think we will change the new Zoom. Easier. Okay, see you in 5 minutes time.
Okay, sure. Okay.